And here we are, at the end of our lovely little excursion into kernels. This video will give another example of using kernels, as well as summarize some of the important topics to take away from this lecture series in general. Let's get back to the idea of radio basis functions for function approximation. A very popular kernel is the Gaussian kernel. It has the same functional form as the Gaussian RBF and the same properties. However, there is a slight difference, which can be seen from the prediction function. While we could choose the centers of the bumps with the parameters when we were using the Gaussian RBFs, the centers are now fixed by the training samples when we use the Gaussian kernel. Let's check out some examples. The red points were generated using a linear function with superimposed noise. The blue line is the result of a linear regression using a Gaussian kernel. The key to getting good results with the Gaussian kernel is to pick a suitable value for the variance. If it's too small, as in this plot, the approximation follows the data points and therefore the superimposed noise too closely. In other words, it overfits. With a larger value for the variance, or a larger value for sigma, we see that the approximation gets much more reasonable. But notice, we still have these problems at the end where we don't have data points. Remember how we discussed this earlier in the lecture series. As sigma grows, our estimator calculates the mean over too large of a range, and this means that it doesn't follow the trend of the original function. When the variance gets really large, the estimator is super biased towards a flat line with the value of the mean of the dataset. Thus, we have the old bias variance dilemma all over again. So how do we deal with it? As always, a good method is to use a simple grid search on the hyperparameter sigma, and then use cross-validation or a separate validation set to test a particular value of sigma. Back a couple of slides, I pointed out how the ends of the function that we were trying to approximate tailed off in a direction that it's not consistent with the linear function that generated our data. This is a problem because we were using Gaussian functions. One way of solving this is to make a combination of kernels. So what we could do is we could take the Gaussian kernels that we have already calculated, and we could combine them with a generic kernel called k sub 2. Here, that k sub 2 could just be a linear model. The linear model then computes the general trend of the data, but the Gaussian kernel helps capture the local variations that might occur. So if we were to combine this with a linear model, it would help us to extrapolate better on the ends where we don't have data points. The most common kernels are the linear, polynomial, and Gaussian kernels. Note that the polynomial kernel is different from the kernel that you get from a polynomial basis, but it's mostly also used in language processing, in natural language processing. A typical value for the degree is 2. Higher values usually lead to overfitting. The Gaussian kernel is mostly used for regression and classification using support vector machines. We've already seen a regression sample, and we will see a nice classification example using Gaussian kernel when we discuss Gaussian processes. Sometimes people also use functions that are not positive semi-definite as kernels. In many cases this works, however, beware. It might lead to strange results because the underlying assumption of regression or the classification algorithm is that it works in the feature space, and this assumption is violated. Many other machine learning algorithms that use scalar products, or that can be rewritten to use scalar products, for example, principal component analysis, can be represented in dual form, and thus kernels can be introduced in that algorithm. Another very, very useful property of kernels is that we can define them on arbitrary domains. For example, we could define a kernel that computes the edit distance between two character strings. Then, we could use this kernel to do classification on strings. So in summary, kernels compute the value of a scalar product in high-dimensional feature spaces, but they don't actually explicitly compute the features themselves. They save that calculation, which saves you time. Furthermore, they can be used in any model that depends on the scalar product of the training samples, or that can be rewritten so that it depends on the scalar product of the training samples. Remember, not every function is a kernel. It has to be symmetric and semi-positive definite. Use the kernel construction rules to prove that the function's a valid kernel, because proving positive semi-definiteness can be difficult with some matrices. I hope you enjoyed the small little excursion we had into kernels, and I hope you keep this in mind as we discuss about future algorithms such as Gaussian processes and neural networks, and other types of classification or regression models. How could kernels be used to do the same task? They're really ubiquitous. Well, thanks for watching, and have a great day.